Tutorial 2 question 2. Alright, let's do something about the sandwich panel again. Alright, so it is a very tedious process and it's very complicated if you don't know the key concept. And therefore in this video we'll likewise like other tutorial videos, we'll talk about introducing the question first, allowing you to fully understand what the question is asking. Then we'll finally know what to apply in our formulas and how to use them to get our answers. Okay, and therefore let's start. So the figure 2 shows a symmetric transverse section. So this figure 2 shows a symmetric transverse section. So it's talking about a cross sectional of your beam. That's all. Alright, showing a cross sectional of your beam. Okay, so your beam, if happen that you don't understand still, where's my pen? Yeah, this is the beam. Alright, 3D. So a cross sectional is just a cross sectional of your beam, that's all. Okay, hopefully this is pretty clear. Alright, where the faces are made of woven rovings. If you remember, the faces of your sandwich are these faces and this one. Alright, while the composite so the faces are made of composite laminate, woven roving, and polymeric foam core. Alright, polymeric foam core, the core is the in between this green color one. Alright, and both laminates are running at a angle of plus minus 45 degrees. So both of the laminates are in, so both of the faces are running in for the plus minus 45 degrees. Alright, each of the bidirectional means two direction laminate, alright, is made of two identical plies. Alright, so each of the, so individually this face, each of this face has two plies. Alright, has two plies. Very chim, right? It's more and more complicated. So if the section, where's my section? Yeah. So if the section is subjected to shear force of 200 newtons, then I'll ask you to find the maximum stress at the interface between the core and the face. Alright, so the interface is actually being between the this thing. So they're actually looking at this interface. This line is the one they're looking at. So they're actually looking at the shear force. So they're looking at the maximum shear stress acting on this two interface, or this red color one. Alright, that is just what the meaning it is. And therefore the equations is being provided for you, which is this one. This is the equation that we have seen in the previous video where we talk about, or previous two videos where we talk about a sandwich shear stress. Alright, this is in fact our Q. Alright, is it our Q? So this is the equation that we have discussed earlier in the previous two videos. This is the Q, this is the V, they are actually the same. Alright, V is the shear force, Q is also the shear force. It depends on how you actually look at it. Alright, for the rest I'll not go into details. Alright, these are all the things that we have gone through. Alright, so I'll just touch on a little bit about the woven rovings, alright, that of thing. So if you were to head back to your lecture note part 1, page 82, alright, your roving is what we call like your threaded stuff. Alright, so there will be a certain threads all around. So once you wove it, or once you weave it, alright, once you kind of like put them together, you'll get it as a woven roving. Alright, so you wove the rovings with all the threads, or you wove it up to become like this. So woven roving is somewhat this somewhat checker type of thing. To be more exact, should be something like this. It can be this type. This is a weave fabric. This is also another weave type of things. But in terms of different weave, balance weave, setting weave, and things like that, which we have gone through previously. But then you know that the woven roving is in terms of this form, while your unidirectional is in terms of this lines all over here, as you can see, right? Back here, you are talking about woven rovings, alright? And we are taught to actually calculate things in terms of a unidirectional laminate, which we have done previously, right? In previous lesson, alright, tutorial 2 question 5, alright, we talk about how to find your unidirectional laminate. But now it's a woven roving, so we need to use another formula, or where this formula, this one, okay, you can go to your reading material page 44, alright, which we haven't go through yet, but we will go through now. Okay, so if you remember your Q11, if you don't understand any of this thing now, alright, you can actually head back tutorial question 5, V6.6. V6.6. I'm talking weird now. Alright, but yeah, you just watch the tutorial, you'll know why do we calculate the Q. Alright, these are all your stiffness matrix, alright, all values. Alright, Q11, Q12, Q13, etc. all the way 3 by 3 until Q33. Alright, and then if you were to transform them using a certain angle, then you'll get the second bar type of thing. I'll not go through into details since that series of videos will talk about it. So you have to finish the tutorial in order to come to this tutorial. Okay, so this thing over here is your woven roving. Alright, so you have to calculate your woven roving using the unidirectional. So we have to first calculate your unidirectional Q, which is what we have calculated in the method that we've calculated using tutorial 2 question 5. Alright, this series from 6.6 onwards. Just go and watch the video. So you'll know how to calculate your unidirectional Q. Alright, and unidirectional Q bar. Once you know all this, then you will sub it in to get your woven roving's value. Okay, and then eventually the transformation type of stuff. Okay, so therefore our first step is to find your Q again, alright, and your Q bar. And then the second step is to convert into, I should say that now is unidirectional, right? So I should come to saying that it is actually a woven roving now. Bar. Okay, so this is the first step, this is the second step. Alright, what is the purpose of us calculating that? Because we want to calculate for the modulus of elasticity. Alright, if you think about it, your face over here, alright, its Young modulus E, or normally if you remember in the previous video we talked about the SE, this SE over here, alright, is in terms of the Young modulus of your face and your Young modulus of your core. Alright, so therefore your Young modulus of your face is in terms of a smaller stuff, is a laminate type of thing, right? So therefore you're gonna calculate your Q. So once you calculate your Q already, then you're gonna calculate your axial stiffness. Alright, and eventually you can calculate your longitudinal X, your Young modulus elasticity, alright, which is also in that video. Alright, in all this is similar stuff. Alright, it's similar stuff, it's not totally in the video, but the formulas and the applications are all the same. Alright, so our purpose is to calculate for your ELX. So this ELX will be the Young modulus for your face, for your Young modulus of your face. Okay, so the properties of your material is given, the Young modulus of your fiber and your resins are given, but it's talking only about one laminate only. So if you have two laminates, then if you were to set them up together and find the total Young modulus, it will be your ELX. I hope that this is very clear. Alright, so the Young modulus for your fiber is just your fiber, that's all. Resin is just your resin. But because your face is comprised of two laminates, which has each laminate has one fiber, each laminate has fiber and resins, then you know it's getting more and more complicated. Alright, so therefore please take note of this. We want to calculate for ELX in order to calculate your face. Alright, your face of your so-called your sandwich panel. Now this is the only part that is very complicated. Alright, that makes you feel like what the hell is going on. So this is the part. So once you clear this part, once you find that, we can somewhat say that we are somewhat safe. Alright, because this is the exact same equation that I'll be using later on. As a whole system, alright, I can't zoom in properly, alright, but as a whole, once you get our ELX already, this ELX is actually your EF, your Young modulus of a face. Alright, where this is all, in fact this is exactly as this thing, but this is easier, it's a more clearer because this one is a bit corrupted. The words are being blurred. So you can simply use this equation to calculate for your stuff. Okay, so this is the whole thing that is quite important, and it's pretty straightforward once you get this ELX, which is the first issue that we are talking about. Alright, so once you get that, alright, you just sub in your ELX, and where your EC is your Young modulus of your core, which is also given, or Young modulus of your core is given, so you just simply sub in only. Okay, and D, if because you're finding your shear stress, right? So your D is your flexural rigidity, alright, which is flexural rigidity, and you're gonna just calculate the same thing again. Alright, so it's the Young modulus of your ELX again, things like that. So you need to calculate your ELX first, while the BT, your BTD square, your BC cube, all everything is based on this thing. So you need to know how to actually set up this which is the B, which is the C, which is the D and H. So once you know how to set up these things, alright, it's pretty straightforward already. So the second part over here is just to apply the formula. That's all. Alright, so the first part, alright, the first bigger part is this one. Find your ELX first. Once you find ELX, and the purpose of ELX is to find the Young modulus of this face, these two faces. Okay, so once you find that, then you can sub in into the equation and eventually to find your shear stress, which is what the question is asking. Okay, so along the way we may see some problems coming up, alright, because my writing sucks, so when I copy wrongly, but nonetheless here and there the concept should be alright, I guess, and therefore yeah, and I shall see you then in the next video to start to calculate the first part of your stuff. Okay.